So welcome you all for another session on module 1 of mechanics of materials. Today I intend to derive a relationship between the elastic constants, Young's modulus of elasticity, modulus of rigidity and bulk modulus. Okay, that's what I intend to discuss, and these are the points which I have written already. Hooke's law, you all know, and Hooke's law, when we apply it for normal stress, we can express mathematically like this: E is equal to sigma upon epsilon, the normal stress and normal strain, and this is what is called as the proportionality constant, Young's modulus of elasticity. And similarly, Hooke's law, when we apply it for shear stress, we call it as G. The modulus of rigidity is equal to the shear stress divided by shear strain phi. And we haven't discussed much about the shear strain. Anyway, no problem. And I shall introduce you again the shear strain. And these two expressions, mathematical expressions, they indicate Hooke's law. And of course, these are valid only within elastic limit. As long as your stress sigma and tau are within the elastic limit, and then only they are valid. Then we also have what is called as one more definition of bulk modulus. Bulk modulus is equal to sigma upon epsilon v, and of course this is again valid here also. This also is valid within elastic limit. So again, I shall go again when I start discussing the relationship, and if required, then I shall revise what is meant by K, or how do we define K. K is equal to sigma upon epsilon v. What is sigma, epsilon v, etc. I shall revise it once again. Okay, as I said, I want to really relate this. These are all constants for a given material. Okay, so E, Young's modulus of elasticity, modulus of rigidity, bulk modulus, and this is Poisson's ratio. All these are constant for a given material. That is why we call them as they are the properties. We say that they are all related. Okay, so if X and Y are brothers, then we say that they are related. Like that, these are also related. What is the relationship between them? How they are related? Okay, that I want to derive, and my derivation is going to be in these three steps. First, I shall be deriving the relationship between E, G and mu. Young's modulus of elasticity, modulus of rigidity, and Poisson's ratio. Maybe in the next step, E, K and mu I shall relate. Okay, I can make use of these two and eliminate mu, and this is how I can get the relationship between E, G, K. This is how I am going to do it. Okay, so I would like to start with the first relationship, what is called as relationship between E, G and mu. Okay, so for that I consider a body. Please see that it is not a thin paper like this. It has also the perpendicular dimensions. It has a body which is subjected to planar forces. The forces are only in say XY plane. Let me call this board as XY plane. Maybe this is X axis, this is Y axis. This plane is called as XY plane. Okay, these forces, a number of forces, the magnitude, etc. I am not worried about it. And this is a body which is subjected to planar forces like this. I want to consider what is the stress at this point. The stress at a point is expressed by what is called as state of stress. How do we express? By imagining a cube surrounding that and expressing the stresses acting on all the faces, all 6 faces of the cube. And fortunately we are dealing with only planar forces, only X and Y, and we don't have forces in the third direction. So therefore we shall not be having stresses in the third direction, which happen to be Z direction. We shall not have any normal stress or shear stress, that kind of thing in Z direction, and therefore I want to imagine a cube. Okay, a cube which I intend to show it like this. Okay, it is a square. Okay, so it has perpendicular dimension also, and whose side is also equal to the same as this. That is here AB, and it is same as BC, and it is same as CD, and it is same as AD. It is same as the thickness, the perpendicular dimension. All the sides are equal. Okay, so since it is we are talking about 2D, 2-dimensional, therefore the diagram also, whatever I am having 2-dimensional diagram, and therefore I am happy with that. Okay, so A, B, C, D is the face what I am imagining, something like this. I am imagining, and there is a perpendicular dimension, and the same thing I have shown it like this, and enlarged this thing. Okay, this is before the application of any load. Okay, and once I consider the load, so what I do is I cut it like this, then I cut it like this, I cut it like this, I cut it like this, and draw the free body diagram every time and show what are the stresses acting on all the faces. That's what I do. And I assume, for my convenience, I shall assume that this is subjected to only pure shear. Pure shear, I hope you understand. On any plane, if you have only one type of stress, that is called as pure shear. Okay, let me assume that it is having a shear stress in this manner. Okay, so let this be equal to tau. As you all know that if you have shear stresses on one pair of faces, then the other pair, on the other pair, it comes automatically free, complementary, and therefore you have a shear stress like this. Okay, this also is equal to the same magnitude. That is what I call it as tau. Okay, so I have assumed. How did I get this? Actually, so it all depends upon what are these values, etc. And for my analysis purpose, I am assuming that let the element be like this, and these are the stresses. Okay, the moment you have stresses, these stresses, what happens? This A, B, C, D, which was square earlier, this face, and it won't remain a square now. Okay, what happens? If I hold it, I shall assume that this has been fixed as if the same thing applying here or fixing it. I hold it, and what happens to this face, and this face? This face will slide, and B probably will move to this point, and which I call it as say B1, and C will move to this new position C1. Okay, and this face A, B, C, D, which was square earlier, now it is going to become something like this: A, B1, C1, and D. It becomes like this. This is my new face, new shape. Okay, so the shape has distorted. It is no more square, and therefore the stress what is responsible for this is also known as distortion stress. Okay, so earlier this AB was perpendicular to AD. Now the new edge AB1 or new face AB1 is not perpendicular, and there is change in the angle. This angle is, I am referring it as phi, and normally this side also is same, and this phi is called as shear strain. Phi is what we call it as shear strain. Okay, it is very easy with respect to the normal strain. The change in the dimension divided by the original dimension is strain. Okay, here the change in the angle, which was earlier 90 degrees, and how much it has decreased, that angle is called as shear strain. Okay, so now, so this is A, B1, C1, D. This is my new shape. Now what I want to do? So as I said, I want to find out the relationship between E, G and mu. Okay. So now how do I start here? Okay. So I have two faces A, B, C, D. This is the earlier face before the application of the stress. Now A, B1, C1, D. This is the new face. Okay. I just make a certain construction. Say I shall draw what is called as AC, the diagonal AC. This is AC, and I shall also draw one more. This is AC1. AC1. So please remember, only to make the things clear, I have shown phi value as if it is large. Phi is something like that. I have shown around 20 degrees, 30 degrees. But in real sense, for a real material, okay, it is hardly couple of degrees or less than that. So the value of phi is very small. Please remember that, because I should be using that. Okay, so looking at the diagram, what is the angle A? Not A, it is BCA. So BCA, how much is that? You all know that it is a 45 degrees. Similarly, what made the angle B C1A? Angle B C1A. Okay. Do you agree that it is almost very close to 45 degrees? Because this B1 or C1 is very small, and therefore this also is equal to very close to 45 degrees. Please remember that. Okay. So now what do? I want to find out the normal strain. Okay, though it is subjected to that. What is normal strain? Normal strain, what is the change in the dimension divided by the original dimension? So I want to find out something like this. The epsilon, normal strain, in what direction? Along the diagonal. Epsilon, I call it as epsilon AC. I want to find out the strain, normal strain of the diagonal AC. So this is what I want to find out. So what is this definition? What is the new dimension? What is the new dimension? New dimension is AC1. And what is the original dimension? AC. And if I find out the difference between the two, what do we get? What is the change in the dimension of the diagonal AC? And divided by the original dimension, which is called as AC. Okay, so this is what I call it as epsilon, the strain along the diagonal AC. Okay, so now this is equal to, okay, what is that? AC1. Okay, I shall make one more construction here. From C onto this AC1, I draw a perpendicular. And call that point as X. Okay, so now AC1, can I write it as AX plus XC1? AC1 is nothing but AX plus XC1 divided by, it is only AC1 minus AC, with the whole thing divided by AC. Okay, so now please remember what made the angle between CAC1 very small, maybe 1 degree, 2 degrees or less than that. Okay, so similarly here I have something like this. Okay, so here I have two lines, one is PQ, the other one is PR, and I have PQ is equal to PR. I have taken the same length here also, and this angle is substantial, very high, something like 60 degrees, 70 degrees. I have dropped a perpendicular to this on this R1, and PR1 is equal to this, whatever, if this is theta1, something like this, then if I write cos theta1 is equal to this divided by this or in other words, PR1 is equal to PR cos theta1. Okay, if theta1 becomes very small, as I have there, okay, I have the CA, this C1, the angle between the two is very small. If it is made very small, if I make it half like this, say again PQ is equal to PR, I would like to take, say something like this. Then drop it perpendicular to this, something here. Okay, if I reduce the angle, now PR1 or whatever this perpendicular, whatever I draw now, it has increased its length. Then again you reduce the angle and make it very small. In that case, whatever the perpendicular drop onto this and this. So what I mean here is AC and AX, they are almost same. The angle between CAX is very small. In that case, the distance AC and AX, they are almost same, and therefore AX I can replace it by what is called as AC and plus XC1 minus AC divided by AC. So what is this AC? AC is the diagonal of this square, which is nothing but square root of, I can write it as AB square, not YAB, AD square AD square plus CD square. AD square plus CD square. I will reserve this space for this analysis. I will continue here. Okay, this is epsilon EAC, and I shall simplify this, and finally I write it here. What is that? Epsilon AC is equal to this AC and this AC cancels, and this XC, I shall write it as it is, divided by, I know that AD and CD, both of them are equal. This is what I have assumed, AD is equal to CD. So this is equal to AD is CD only, CD square plus CD square. This is nothing but square root of 2 times CD square. So this is nothing but square root of 2 times CD. 2 times CD. Okay, so now XC I would like. So take this. This is XC. This is XC. Okay, so I have in this triangle C1, CX. XC1C. What is the angle XC1C? XC1C. Do you agree that it is very, very close to 45 degrees? So angle XC1C is very, very close to 45 degrees. I can take it as 45 degrees. Okay, therefore cos of 45 degrees, cos 45 degrees, okay, is equal to XC1 divided by, I know that this is 90 degrees, and therefore CC1 is hypotenuse. So this is 45 degrees, cos 45 degrees is adjacent side. This is nothing but XC1 divided by, what is that? Divided by CC1. And therefore XC1 is what? XC1 is equal to CC1 into cos 45 degrees. What is cos 45 degrees? It is nothing but 1 divided by root 2. Okay, now I shall substitute here. This is XC1 now. Yeah, XC1. XC1. And therefore epsilon AC, I have come to almost the last page, is equal to XC1. What is XC1? It is CC1 divided by root 2, the numerator. And what is the denominator? That is root 2 times CD. Okay, so now root 2 into root 2, that becomes half. And CC1 divided by CD. Go back to the triangle. CC1 divided by CD. CC1 divided by CD is nothing but tan phi. So therefore, this is nothing but tan phi. And I know that, I am sure that the phi value is very, very, very small. And when phi is small, tan phi is same as phi. And therefore, this is phi, tan phi is phi divided by 2. Okay, so now I shall make use of this space. Okay, I hope I can rub it, and then because the ultimate result, whatever I get from this analysis, I would like to write it epsilon AC is equal to phi divided by 2. Go back to the definition. Phi. What is phi? Phi is equal to tau divided by g. This is equal to phi is nothing but tau divided by 2 times g. So this is what I obtained the relation. The diagonal, normal strain in the diagonal is tau divided by 2 times g. Okay, this is what I have derived it from. And now go back to the original problem. What is the original problem? The problem, a body which is subjected to the planar forces, and I am trying to find out what is the stress at this point. As I said, I can imagine a cube and express the stresses acting on that cube. You will get what is the state of stress at that point. How many ways are there to express that? Theoretically infinite, because I can have the cube orientation in any manner, and accordingly I can express the state of stress at that point in a different way. So that's what I would like to do. I would like to imagine the element in this way now. Okay, so earlier the same size cube, okay, whatever I had here, okay, I don't want to change the dimension of that. The only thing is I want to rotate this 45 degrees, or in other words, say the B, say I will take one face like this and another one like this, another one like this, another one like this. Or in other words, B is the midpoint like that. Okay, B is the midpoint, D is another one, and this is C, and this is A. Just to compare here. Otherwise, you can name some more points and then accordingly. But size, everything same. So go back here. Okay. So what is happening to the diagonal AC? Just look here, and it has become AC1. The diagonal AC, it has become AC1. Whether its length has increased? Yes or no? This was AC, and now it has become AC1. The length has increased. And what do you feel about the diagonal BD? Earlier it was so much, now it is so much. The diagonal BD has compressed. Okay? And therefore I can apply that logic. So I feel that, okay, this diagonal AC, as if it is subjected to tensile stress, and which I call it as sigma AC. And similarly, along the diagonal BD, what is happening? Its length is being this thing, and therefore this side is being compressed, and therefore here I have what is called as sigma BD, which is compressive stress. Sigma BD, the diagonal BD is being compressed and AC is being pulled. Sigma AC and sigma BD, these are the normal stresses. And one more thing, I can easily prove it, and that requires the help of module number 2, which I am going to learn. And I can show that sigma AC is also having the same magnitude as the tau. Please remember, the magnitude of sigma AC is same as that of tau. Okay, or in other words, let me write down here. This is equal to tau, and this sigma BD, the magnitude, is also equal to tau. How do I say it? So here, as on now, I don't have any mathematical proof unless I teach you module number 2, and I can show that this C is equal to tau. This is compressive stress magnitude. Tau means shear stress, but remember it is actually subjected to the compressed stress, and its magnitude is equal to tau. And similarly, sigma AC magnitude also is equal to tau. So this side it is being pulled, and this side it will be compressed. So now again I go for what is epsilon AC now? What is the strain in the direction AC? Okay, the strain in the direction is because of two types of stresses. Two stresses, not two types, two stresses. One is because of sigma AC, and the other one is because of sigma BD. Sigma AC pulls it in this direction, and therefore sigma AC strain and the strain in this direction AC, they happen to be longitudinal stress, and therefore it is equal to sigma AC divided by E. AC is only suffix, sigma suffix AC, sigma along AC. Okay, then I am interested in the strain in the direction AC. I also have strain because of the sigma BD. The strain in the sigma due to sigma BD in the direction AC. Okay, is it plus or minus? This is being, in this direction it is being compressed, and therefore in this direction it is being enhanced. Therefore it is plus. Plus what? What is this strain with respect to this? That is lateral. That is nothing but mu into sigma BD divided by E. This is what is generalized Hooke's law. Okay, sigma, if you take this as x direction, this is y. Sigma y is minus tau. Please remember, sigma y is minus tau. That is why you get here plus. Okay, if you want to know what is sigma BD, in that case, this also is minus, this also is minus. Anyway, that I don't need it. So I shall substitute. What is sigma AC? Sigma AC is tau by E. So this sigma BD is also tau, and it is compressive. That is why I have already taken into sign. So if I tau divided by E, I shall take it separately common. Tau by E, this is 1 plus tau by E, this is mu. What is this? Epsilon AC. The strain along the direction epsilon AC is given by this. The strain along the direction epsilon AC is also given by this. Both of them must be same, and therefore the equator of the two. What is that? Tau divided by 2g is also equal to, what is that? Tau by E. Tau by E into 1 plus mu. We simplify tau and tau cancels. Cross multiply and write down what is called as E equal to 2g into 1 plus mu. This is what is the relationship between E, G and mu. I hope you understood. The relationship between E, G and mu. E is always equal to 2g plus into bracket 1 plus mu. If you know E and mu, you can easily calculate G. If you know G and mu, you can easily calculate E. If you know G and mu, you can easily calculate E. So that means any two of them, if you know, you can easily find out the third one. This is what I mean by this. This I have done. Okay. Now let me proceed to the second one. Okay. And compared to the amount of effort, time, etc. required for this, the remaining things are very simple. Okay. E K mu relationship is very simple compared to all this. The second one, what is that? E, K and mu. What is K? Bulk modulus. How do we find out the bulk modulus of a material? Bulk modulus of a material, how do you find out? What do? I take a cube. This is a cube, solid cube made of the material whose bulk modulus I want to find out. Okay, it is a cube. So how many faces are there? 6 faces. And what do I apply on all these 6 faces? The same amount of stress. The same amount of normal stress in this direction. And also in this along Y direction. And also along Z direction. Sigma x E is equal to sigma. Sigma y E is equal to sigma. And sigma z is also equal to sigma. On all the faces, I apply the same amount of stress. Okay, why do I do it? I want to know, I want to find out what is the bulk modulus of this material. Okay, so I do all that. Then K is equal to sigma divided by epsilon V. That's all. Okay, so now, I want to apply this definition. So sigma I already know. Epsilon V, what is epsilon V? Epsilon V is equal to sigma x plus sigma y plus sigma z. Okay, so here sigma x is equal to sigma y is equal to sigma z, which is equal to sigma. So what is epsilon x? Epsilon x is equal to sigma x by E minus mu into sigma y by E, which is also sigma, minus mu into sigma z by E, which is also sigma, mu into sigma by E. This I shall write it as sigma by E into 1 minus 2 times mu. And if you write what is epsilon y, this also is same as epsilon z, which is also same as this. Yes or no? I shall write you one of them and show you. What is that? Epsilon y. Okay, first due to sigma y, that is nothing but sigma y divided by E, this is longitudinal. And due to sigma x, it is lateral, therefore it is minus mu into sigma x by E. Then sigma z for sigma y, lateral, Therefore, it is minus mu into sigma z by E. I shall replace x, y, z, all of them are sigma only. If I take sigma by E, 1 minus 2 times mu. Therefore, this is also equal to epsilon y and this is also equal to epsilon z. Okay, so now I would like to find out what is that epsilon v. Epsilon y is equal to, okay, I have made a mistake here. What is this? This is not sigma x, epsilon y, and this is epsilon z. Okay, epsilon v is equal to, add this. This is epsilon x, epsilon y, epsilon z, all of them are same. This is equal to 3 times epsilon x. This is equal to, so 3 times sigma by E into 1 minus 2 mu. Okay, so what do I have done so far? I have applied the definition of bulk modulus, nothing else. Bulk modulus, how is it defined? Take a cube made of a material, apply the same stress on all the faces, and then the ratio of sigma to the volumetric strain. Okay, I want to find out the volumetric strain. That's what I have done. And go back now to the definition. K is what? Sigma divided by, what is epsilon v? This is 3 times sigma upon E. That E will go here into 1 minus 2 times mu. Sigma and sigma cancels. You can cross multiply and what they have. E is equal to 3 times K into 1 minus 2 times mu. This is the relationship between E, K, mu. This is what I mean by this. The relationship between E, K and mu. Okay, both of them have been obtained now. Now only a couple of minutes to get the relationship between E, G, K. Okay, to do that, first I shall write down what is the relationship between E, G and mu. E, G and mu. What is that? E, G and mu. E is equal to 2G into 1 plus mu. Then I also have it called as E is equal to 3K into 1 minus 2 mu. 1 minus 2 mu. Okay, very simple. So from the first one, I will get rid of mu. The very purpose is I don't want mu. Okay, so here I can write down E upon 2G. 2G bring this head. What is that? E upon 2G equal to 1 plus mu. E upon 2G minus 1. What is that? This is equal to mu. Similarly, a similar thing here. E upon 3K. E upon 3K is equal to 1 minus 2 mu. Send that, okay, 1 also to this side. This is minus 1. This is equal to what? This is minus 2 mu. Okay, so multiply throughout by minus sign. Then we have 2 mu is equal to 1 minus E upon 3K. Or I don't want 2. So therefore mu is equal to 1 by 2 minus E upon 6K. Is it right? Okay, this is mu and this also is mu. Okay, equate the two. What is that? E upon 2G. I shall take simplification. 2G. Okay, E minus 2G. This is what? E minus 2G upon 2G. That is equal to mu. That is also equal to 12K or not 12K. 6K is substitute. 6K. 2 and 6K LCM. 6K. It is 3 times K. 2 into 3K minus 6K is already there. It just E. Okay, cross multiply. So E into 6K, or you can simplify this. 2 1s are and 2 3s are. Okay, cross multiply 3K into E. Okay, 3 times EK. Okay, minus 2G into 3K. This is minus 6 times G into K. Okay, equal to 3gk, and g and e, this is minus g into e. I would like to take all e terms. I would like to write final relationship. E is equal to what? Okay, therefore this GE and this term I shall have it one side. Anyway, this is GK, this also is GK. So this is 3K plus GE plus GE. If I take E outside, this is 3K plus G. This is equal to 3GK and this plus 6GK. This will be 9 times GK. Therefore, E is equal to 9GK divided by 3K plus G. Okay, we have a relationship between E, K and G. Okay, so if you know any two of them, you can find out the third one and find out all the constants, and this is how they are related. Okay, so based on this, you have normally numericals also, and therefore you can easily solve them. It is more of substitution like problems, nothing much thinking, and you need to remember these expressions, and many times the derivation is also asked, and therefore you should know that also. Yes, good day.